Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Juan Ignacio Espinoza-Retamal with us today. Hello, Juan.
Hi Frank, how are you doing?
I am doing awesome on this October 1st of 2025 as we record this. Juan, what's your geolocation?
Well, I'm currently in a small city in the central regions of Chile,
Nice.
named Constitución.
Cool.
I actually defended my PhD thesis last week, so I'm at my parents' house right now, having some rest, chilling a bit before going to the postdoc stuff.
Well, congratulations, Dr. Juan. That is awesome.
Thank you.
Very cool. Very, very cool. Let's see. Yeah, so that's Southern Hemisphere. So you're probably in your winter mode there a little bit.
Yes, it's been a unusually cold winter here in
Oh,
Chile.
okay. Okay. So is the little town you're at, is it closer to the coast or is it closer to the mountains or is it in the mountains?
Yes, it's right on the beach. Yeah.
Right. Uh, I should come visit you. So I'm in Phoenix and Northern Hemisphere, and we are definitely in our summer mode. So we're hitting the 40
Oh,
Cs, 41 Cs, somewhere around there. So yeah, we're quite a bit different. Very cool.
yes, sounds like super hot there.
It's super hot. Even at like 5 in the morning, it's really warm outside. So yeah, but
Oh.
it's all good. It's all good. Let's see. And what do you like to do for research?
Well, actually, I'm in the field of exoplanets, so I will say everything through detection, characterization, and then orbital dynamics, stuff
Cool.
like that.
Very cool. Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. Go grab a copy for free. Go get one. The spin orbit alignment of 8 warm gas giant systems. And Juan, take us away.
Yes. So first, I would like to say thanks to all my co-authors. This work has been done in collaboration with many people. Most of them have been at a Chilean institution in the recent years,
Uh-huh.
and have been participating in the different aspects of this project. So Andres and Rafael have been basically leading the project with me, writing the proposals and that kind of stuff.
Yes.
Cristobal, then my PhD advisor.
Ah, okay.
Uh,
Okay.
then Eliar played a big role with the observations, performing the observations and doing the data reduction. He's like the expert in the espresso spectrograph.
Nice.
Then we have Gudmundur, aka Gumi.
Cool.
A big part of this work was done during my visit to the University of Amsterdam in the Netherlands.
Oh,
So
yeah.
I had the opportunity to collaborate with Gumi there and his group.
Nice.
Then we have Melissa and Marcelo. They both have been helping with the proposals and more follow-up observations.
Mm-hmm.
And Diego, who has been working with the statistical analysis and dynamical simulations and things like that.
Mm-hmm.
And finally, we have Gavin, Rodrigo, and Vincent that helping obtaining some simultaneous photometry of the observations that we perform here.
Very nice. Beautiful shout out. Very good. Very good. Okay, let's roll.
Yes, so I mean the title is The Spin Orbit of 8 Warm Gas Giants. So this is a paper about spin orbit measurements. Uh, spin orbit, also known as the stellar obliquity, is the
Hmm.
angle between the stellar spin axis and the orbital axis of the planet in a planetary system.
With you.
Or if you want a more intuitive way to think about it, it is the angle between the orbital plane of the planet and the stellar equator.
Yes. Okay. Hmm.
And well, for you to have an idea, in the solar system, this angle is like 7 degrees between the ecliptic and
Uh-huh.
the sun's equator. And it's kind of important because it can give us, or we can learn about the dynamical history of a system using obliquities.
Okay.
That's the importance of the angle.
Yes. Okay.
So this paper studied the angle in other planetary systems, not our own solar system, and in particular is for system with warm gas giants.
Ah, okay.
So as the paper says in the first paragraph, I think, ever since the discovery of 51 peg, we
Yep.
have some open questions about the formation of, I would say, close-in gas giants, including hot and warm Jupiters.
Yes. Yes.
And there have been many mechanisms proposed for their origins. We
Mm-hmm.
can divide them basically in two big groups, one being high eccentricity migration,
Yes.
basically the idea that the system can go crazy and some planets can end up in really eccentric orbits, and then
Uh-huh.
they will migrate eventually due to tidal interactions with with the star.
Yes.
And the second one is basically disk migration, or that the planet form in situ. I think the in situ part is mostly roll out due to observations, but the disk migration is something that we still think it's important. And for warm Jupiters, as we will see, it will be important.
Cool. Okay.
Yes. So if you can go now, scroll a bit down.
Uh-huh. Sure. Summary of our observations here.
Yes, let's talk first about the what we have seen in hot Jupiters
Okay.
and why it's important to talk then about warm gas giants. So for hot Jupiters, we have basically a dichotomy around the Kraft break in the obliquity
Mm-hmm.
distribution.
Mm-hmm.
Uh,
Yes.
Above and below the Kraft break, the obliquity distributions are different. So
Okay.
above the Kraft break, we have a lot of misaligned systems,
Yes.
while below the Kraft break, they are mostly well aligned.
Okay.
And the history then is that hot Jupiters are likely formed through the high eccentricity migration channel.
Yeah.
But due to that hot Jupiters have or suffer strong tidal forces, they can eventually realign with the star. So it doesn't matter what the original misalignment was,
Right.
due to these tidal interactions, they get realigned.
Okay.
So, and that's uh, that's why we care about warm gas giants, because they
Yeah.
are less affected by these tidal interactions.
Mm-hmm.
So the distribution there is more pristine.
Okay. I'm with you.
And then, yes, so, and the problem with warm gas giants is that, well, they are more difficult to detect because they have less frequent transits than hot Jupiters because they
Mm-hmm.
have longer orbital periods.
Mm-hmm. Mm-hmm.
Then also the transit probability at farther out distances is lower, so you have less systems to study.
Yes.
And also because the transits are longer, you need more time, and
Yes.
we know that telescope time is expensive.
More tax proposals. Yes. Mm-hmm.
Yes.
Okay.
So those are kind of the problems we're facing with warm gas giants.
Yeah.
But nevertheless, people has been doing the effort, and we have some measurements of warm gas giants.
Mm-hmm.
And surprisingly, all the systems there, all the warm gas giants are well aligned.
Uh-huh.
So this is maybe pointing towards like a different formation mechanism for hot and warm Jupiters.
Yes.
But the problem is that we need more measurements, basically.
Good.
As I mentioned there in the article, the samples in the literature were of about 12 planets or something like that.
Yeah. Yep. Mm-hmm. Yep. That was Rice et al. Mm-hmm.
Yes. So basically, the idea of this paper is to extend the sample there and
Nice.
measure this for more warm gas giants.
Nice. Very good. Very good. Okay.
So I think now we can go to the table one,
Sure.
because in this paper we observe 8 systems, or the transit of 8 systems, with the espresso spectrograph. So there you have all the systems, and we actually observe one of them, A2329AB.
Mm-hmm.
We observed that target twice, so that's why it is twice in the table.
Mm-hmm.
And here I just want to mention the precision that we get with the espresso spectrograph, the
Ooh.
sigma RV.
Mm-hmm.
In all cases, it's close to 1 meter per second,
Nice.
even smaller in some cases. So
Nice.
espresso is really it's
That's
a really
impressive.
precise
Yeah.
spectrograph. Yeah,
That's
it's kind
impressive.
of impressive.
Very, very cool. Okay. No good.
Yes.
Yeah.
So maybe
Mm,
now you can go to the figure one.
okay, very good. Okay, let's slide on down. There's our transit spectroscopy, and here we go.
Yes. So those are the actual espresso measurements of the radial velocity during the transit of the systems.
Hmm.
What you are seeing there, it's called the Rossiter-McLaughlin effect.
Yes.
The Rossiter-McLaughlin effect is just, I would say, is the spectroscopic detection of a planetary transit,
Okay.
and it shows a clear deviation of the Keplerian signal, right? And
Yes.
in all cases, or almost all the cases, you can see the radial velocities going up and then going down,
Hmm.
and that's and the shape, sorry, of the Rossiter-McLaughlin effect is go up and then go down.
Whoop.
Depends on the obliquity of the system, the spin orbit angle.
Hmm.
And you can see the values there in the individual panels, the
Uh,
values of the fit.
yeah, yeah. Okay, here we go. Yep.
Yeah,
Yeah.
and
Yeah.
you have two values there actually, the psi in some cases and the lambda.
Yes.
So lambda is what we diagonally measure from the Rossiter-McLaughlin effect,
Yes.
and that's the projected obliquity.
Okay.
Psi is then the actual angle, the 3D obliquity,
Yes.
and we can convert lambda into psi if we have estimations of the rotational period of the star.
Hmm.
But in cases where we don't have that, then we only have lambda.
Okay. Okay. That explains that.
So that's why some panels have psi and lambda, and some of them only have lambda.
Hmm. A little bit different case here for 2179b, right? There's no big up and big down.
Yeah, exactly.
Almost
That's
straight.
what I was going to mention that that particular system,
Yeah.
we also report a non-detection of the arm effect there.
Ah, got it. Okay.
And you can see it in the constraint for lambda, like it's 22 plus 80 minus 40. So it's
Yeah, it
basically
could be anything.
not constrained. Yeah.
Okay.
Yeah.
I'm with you. I'm good. Yes. Very cool.
Yes. So basically those are the observations. Uh, I wanted to also, if you can go to figure A3.
Sure. We're gonna slide down here a little bit. Let's pop down to A3. There's Appendix A, 1, 2, and 3. Okay, I'm gonna zoom out so we get everything here.
Yes.
There we go.
So
For
that's
WASP
an example.
106.
Yeah,
Mm-hmm.
that's one of the systems we study here. And these are all the observations we use in this article. So we have panel A, the Rossiter-McLaughlin effect that
Mm-hmm.
we just saw in the main text. Then in panel B, we have the out of transit radial velocities of this object.
Mm-hmm.
And then from panel D to G, we have all the light curves that we use.
Yeah.
And I wanted to highlight in panel G,
Yes.
we have a special light curve because that light curve was taken in simultaneous with the express observations. So
Aha.
they are really constraining
Nice.
the egress and egress of the planet.
Yes, right here and right here. Very cool.
Yeah.
Nice and sharp.
So basically, we're sure the transit happened there.
Yeah, right.
And well, for this target, I think it's not important because the transit, the Rossiter-McLaughlin effect is clearly visible there. But then for small amplitude targets, it could be really important.
Oh yeah, yeah, yeah. No, it's good to, this is a good one to show. Very cool.
Yeah.
Okay. So we will slide back up to figure one, wherever we were, figure one.
Yeah. Can you go now, I think, to section 3.3 to talk about the analysis?
Mm-hmm. Okay, we got photometry, orthogonal observations. Then we get into the stellar parameters of the analysis, photometric analysis. Mm-hmm. Do you want anything in particular? You want to go to figure two?
Uh, no, I think just figure, sorry, section 3.3.
Oh, I'm sorry.
Yeah.
3.3. My bad. Okay, section 3.3, global modeling. Okay.
Yes. So basically, for all the systems, we use all the available observations that are in the literature together with the observations we would take. And we use the Ironman package to do a joint fit of all these observations.
Which is open
And
source on GitHub, people. So I always like that.
yes,
Go get it.
Ironman is a package that I developed to actually do this kind of stuff.
Cool.
It's based on packages that are available in the literature. And the good thing about Ironman is that you can use an arbitrarily large number of uh, data sets and different instruments,
Nice.
and the code can handle all of that.
Very good. Cool.
And I would say it's friendly with the user. It's not complicated to use. So
Very
if you
good.
want to
Download
try
it,
it,
give it a try. Give it a try.
yes,
Yeah.
exactly.
Okay.
Okay, and I wanted to talk now about the figure two that you're seeing there.
Yes. Okay.
So within Ironman, we have, or as I just mentioned, there is a difference between the 3D obliquity and the side project obliquity that we
Okay.
measure from the RM effect.
Uh-huh.
With Ironman, you can derive both when you have information about the rotational period of the star, and
Cool.
only the sky project obliquity if you don't have that.
Yes.
So we try to estimate the rotational period for all these targets,
Yes.
and actually for two of them, the two K2 targets, we derive a rotational period based on this periodogram here.
Okay.
So you are seeing the periodogram for K239
Mm-hmm.
showing a clear peak around 16.9 days. And then for K2 329, the peak is around 24 days or
Yeah.
25 days.
Yeah. Mm-hmm. Okay.
So that's an estimate that we have of the rotational period. And then we convert the
Right.
lambda values into side values using
Yes.
this.
Mm-hmm. Good. I'm with you. Cool.
Yes. Uh, so now we should go ahead and show maybe figure four.
Okay, let's go slide down and we get into some of the results. Let's go down to figure four. Oh, yes. Okay.
Yes. So basically, this is a
Uh-huh.
summary of the results here.
Cool.
What you are seeing in the top panels is the sky project obliquity
Mm-hmm.
as a function of the effective of the whole star.
Yes.
And in the bottom, the 3D obliquity for the systems where you can measure the 3D obliquity.
Uh-huh.
And as you can see, the sample of systems with sky project obliquity is way larger than the sample with only the 3D.
Okay.
Sorry, with the 3D.
Uh-huh. Because we need those rotation periods. Uh-huh.
Exactly. And you don't have that for many of the stars.
Yes. Bummer.
And the left and right are single stars and binary systems.
Interesting. Interesting. Okay.
So there the different colors represent different types of exoplanets, hot
Mm-hmm.
Jupiters, warm Jupiters, and Saturns.
Yes.
And then the circles are the values in the literature taken from the EPCAT catalog.
Nice. Okay.
And the stars are the measurements done in this article.
Very cool.
And actually, yeah, that's a typo. In the binaries, we only should have the green star, not all the other stars.
I they're all binaries.
Yeah, sorry.
I smell an erratum coming, so okay, all good. All good. Yeah,
Yes,
so in this one, got it. I'm with you. I'm good.
yes.
Hmm.
So, sorry, and did I mention about the vertical line? The
Yeah.
blue vertical line is the craft break.
Nice. Good. Go crap.
So, for hot Jupiters, the uh, red circles, you
Hmm.
can see in both left and right that there is a clear distinction of the distributions
Yes.
around, above and below the break. So,
Absolutely.
above the break, you have a lot of misaligned systems, but
Yes.
then below it, they are all well aligned.
Yes. Hmm.
And then, if you focus only on single stars, because most of the results here are for single stars,
Okay.
for warm Jupiters, the orange ones,
Yes.
there are no misaligned warm Jupiters around single stars. You
Wow.
have some maybe 2 points at 40, 30 degrees.
Yeah, somewhere in there, right about here. Yeah.
Yeah,
Uh-huh. Uh-huh.
but definitely something that's different than the distribution you see for hot Jupiters.
Oh, absolutely.
You
Hmm.
have clearly there some misaligned systems,
Yeah.
and
Hmm.
that's not the case if you see the binaries, because even though you don't have many measurements, ignore all the stars there, all
Yes.
these circles, you already have some really misaligned circles right there
Yes. Yes.
in the top of the panel, like three more on top,
Hmm. Yes.
like yeah,
Yeah.
those ones. So you have highly misaligned warm Jupiters there.
Absolutely. Above and below the craft break. Hmm.
Yeah, are more. Absolutely true.
Hmm.
So this is also pointing towards a different formation mechanisms for for warm Jupiters in binary systems and in single stars.
Mm, okay.
because the obliquity distributions are different, right?
Quite different. Yeah. And then we got some
So,
Saturns.
yeah, sorry?
And we have some Saturns, the green ones.
Yes. So the thing with Saturns is that they are not, if you only focus on single stars first, they
Huh?
are not as misaligned as the hot Jupiters, but
Yeah.
they are definitely more misaligned than the warm Jupiters.
Yes.
So
Intermediate.
they are, yeah, in between. Uh,
Yeah. Got it. Mm-hmm.
and if you go now to the next figure,
Huh.
figure
Okay.
5,
All right. Put that one in the memory banks. Okay. I'm good. Four. Okay.
because, okay, those are the measurements, right? And
Yes.
now in figure 5, we show the
Mm.
distributions.
Yes. Okay.
So we actually derived these distributions because you can see there you have cos of psi, the cosine of psi in all the panels,
Uh-huh. It's like a phase. Mhm.
and it is a probability density distributions.
Yes.
Okay,
Hmm.
so starting from the values that we just saw in the previous figure, figure 4, for
Yeah.
these different populations,
Yes.
we use this Bayesian methodology to derive the distributions
Uh-huh.
of each of the different populations. So in the first panel, I think that's the most important one for this paper,
Okay.
panel A, you
Mm-hmm.
have the distributions for hot and warm Jupiters around single stars.
Yes. Yeah.
And you can clearly see that there is a peak in both distributions around the cosine of psi equal to 1. So basically
Mm.
aligned systems, psi
Correct.
equal to 0.
Yes.
And then the tails of the distributions are different. For hot Jupiters, the
Yeah.
tail is more or less isotropic.
Mm-hmm.
Uh,
Right. Yes. Cross
uh,
range. Uh-huh.
yes. And the for warm Jupiters, there are no misaligned systems. So you have no tail, basically.
Right. Basically goes to zero. Mm-hmm.
So this is basically confirming that the distributions are indeed different
Uh-huh.
and that the hot and warm Jupiters are different populations,
Yes.
actually, which
Cool.
is something I don't think we, because we started to study warm Jupiters thinking that maybe they are produced by the same mechanism that hot Jupiters,
Yeah.
just that instead of being at 3 or 4 days, they resulted to be at 10 or more days
Right. There's a
of
more
distance.
distant cousin population. Mm-hmm.
Mhm. Yeah,
But no.
but indeed, it seems to be different.
Right.
Yeah.
Mm-hmm.
And then the middle panel, you have the distributions now comparing for warm Jupiters and Saturns.
Right.
Warm Jupiters is the same distribution as panel A,
Yes.
but now it's compared with the Saturns. And also the Saturns seems to be different. They
Mm-hmm.
also have, or they peak towards the alignment, right?
Yes.
Cosine of psi equal 1.
Mm-hmm.
But then the distribution is more broad, I would say. That's the key difference.
Yes. Uh-huh. Intermediate case.
Yeah.
Uh-huh. Very cool. Okay. Nice. Beautiful.
Yeah. So this is, I think, one of the main results of the paper, that the distributions of these different types of of these different types of gas giants are different.
Yes. Yes. Good punchline.
Yeah. So
Ooh, this is
if you
hungry.
go now to the section 5.4,
Uh-huh. Okay.
we
5.4.
can discuss more in detail the different origins of these populations.
Ooh, yes. Okay, figure 5.4. There we go. 5.4. Yes, on the formation.
Yes.
Mm-hmm.
So remember a bit, for hot Jupiters, we saw a distribution that is, we have a bunch of aligned hot Jupiters and then an isotropic tail.
Yes.
So for that isotropic tail, the most likely explanation is high eccentricity migration.
Yes.
The idea that they are formed because of this complicated dynamic stuff going on in the system. And then we launch one of the systems to a highly eccentric and inclined orbit. and then due to the tidal forces, the orbit realign and can then the orbit circularize and can then realign.
Yes. Mm-hmm.
But there's also the possibility that some of the hot Jupiters migrate because of interactions with the disk, and that's because we
Oh,
also have a lot of well-aligned hot Jupiters.
yes. Okay.
So, so the fact that you have strong tidal forces there kind kind of erase that signature of the formation mechanisms. So you cannot distinguish between the migration due to the disk interactions or their realignment. So,
Yes. Mm-hmm. Okay, we'll come back to that point. Mm-hmm.
yep. And then we have the warm Jupiters.
Yes.
So distribution of warm Jupiter show that they are all basically well aligned.
Yes.
So that's pointing toward a different mechanism formation.
Mm-hmm.
And the idea here is that they form in a well-aligned disk and then they migrate it due to interactions with the disk.
Yes. Mm-hmm. Nebular tides.
Yeah.
Yes.
And well, we think also that the disks are well aligned with the star, right? That's an assumption we made.
Okay. I'll buy that one.
Yeah.
Or has a lot of mass, disk less. Yes. Mm-hmm.
Yeah, but the I mean the distribution is not like they are all perfectly aligned. So there
Oh,
is some
yeah.
scattered there. So
Mm-hmm.
that might be hinting that the disks also have some scattered in the alignment.
Mm-hmm. Mm-hmm. Or at least inhomogeneities to drive it. Mm-hmm.
Yeah. And
Okay.
then we have the population of Saturns.
Okay.
Yes. So they are not as aligned as as the warm Jupiters, but not as misaligned as the as the hot ones. So there is some trend there with the mass of the planet.
That's interesting. Okay. Okay.
Yep. And so a possible scenarios involves that whatever mechanism is putting the Jupiters and the Saturns in these closing orbits,
Yes.
there is a dependence there with the mass of the planet.
Mhm. Interesting.
And
Hmm.
possible mechanisms are this idea of a disk-driven resonance between the planet, a companion, and the protoplanetary disk
Ah,
that's evaporating over time,
yeah, that's a secular. Uh-huh.
or that basically a wide orbit Jovian companion excited the inclination of these things
Yes.
and made it migrate.
Yes. Well, I'm with you. Mhm.
Yeah. Okay, so that's I will say one of the main results of the paper, and we discussed the different formation mechanisms for these different populations.
Cool.
So now let's complicate the things a bit. So
Ah,
maybe you can go to figure 7,
okay, figure
the last
7.
one.
Get more complicated here. Okay, looking at sky projected obliquities.
Yes. So that plot is showing the sky project obliquity as a function of the eccentricity of the orbit
Yeah.
for single stars and binaries again.
Okay.
And the color code, it's what it's called the final semi-major axis in units of the radius of the star.
With you. Mm-hmm.
And actually, it's the current semi-major axis times 1 minus e squared. You can see that in the label of the figure,
Oh, sure, sure, sure.
in the description.
Yes.
Yeah, that
Mhm.
quantity right there.
Yes. Okay. Mhm.
So the code is basically telling you what systems are or will be hot Jupiters with enough time.
Ooh, projection. Yes. Prediction.
So basically, the ones that are more purple are or will be hot Jupiters with time.
Okay.
So
Let's see. Yeah. Okay. Okay. I'm with you. Yes, I follow. Uh-huh.
so this plot is basically showing that typical high eccentricity migration mechanisms, such as the Kosailidov mechanism,
Uh-huh.
indeed are playing a role, especially around single stars for the ones that are well aligned. But then there are also other mechanisms here playing roles.
Sure.
So in the for single star systems, what you can see that all the systems with an eccentricity of 0
Okay.
The distributions of obliquity that there is really broad, right? You have,
All over the place. Uh-huh.
yeah, all over the place.
Uh-huh.
But then if you go to eccentricity, let's say between zero point 0.2 or zero point 0.3,
Yeah.
they are not all over the place.
Yeah.
They are more constrained to modest misalignment between, let's say, 50 and minus 50 degrees.
Yeah. Spread
And
there.
then if you go for systems that have obliquities larger than zero point 0.4,
Okay.
they are basically all consistent with being well aligned.
Yes.
So there is some sort of trend here with the eccentricity.
Very nice.
And it's surprising that the most eccentric ones that has obliquities of the order of zero point 0.7,
Mm-hmm.
it's surprising because if these highly eccentric orbits are produced by the typical high eccentricity migration mechanisms,
Okay.
then we would expect them to be misaligned. But indeed, we're seeing that they are
Huh.
extremely well aligned.
Huh. Okay.
So there has to be here a mechanism that is somehow exciting inclinations, sorry, exciting eccentricities,
Yes.
but while maintaining the planet in the same plane. So not exciting the
Hmm.
obliquity of the system.
Okay. Hmm. Hmm. That's interesting. Okay.
And then for binaries, what you see is what you would expect naturally from the typical high eccentricity migration mechanisms. Again, you have
All over the
for
place.
circular systems all over the place, but
Yeah.
then the eccentric ones are also all over the place, more
Wow.
or less.
Wow. Yeah. Mm-hmm. Mm-hmm.
And this is telling you that maybe the binary companion in these systems is playing a role there in the formation,
Maybe.
exciting the obliquities and the inclinations.
Mm-hmm.
Sorry, the obliquities and the eccentricities, both at the same time.
Okay. That raises some ideas. Okay.
Yeah.
Cool. Cool.
So this is basically changing I would say, the Kosailidov panorama that we had in the migration of hot and warm Jupiters,
Yes.
because now we're seeing that there is a mechanism that is not exciting the obliquities; it's only exciting eccentricities.
Yes.
And if you go to section, I think it's 5.3, where we discuss
Uh-huh.
this trend.
Trying
Yeah,
to fast.
no, sorry, it's 5.2.
5.2. Let's slide up a little bit and trend with eccentricity.
Right. So basically, there we discuss what I just mentioned, that there is some sort of uh, relation between the obliquity and the eccentricity.
Okay, good.
And indeed, then we mentioned that we can discard the isotropic distribution of the eccentric warm Jupiters at 8.6 sigma level.
Nice.
So that's basically discarding all the the typical high eccentricity
Yeah, yeah,
migration
yeah.
mechanisms.
Wow.
And there are two possible resolutions to this trend. One is that eccentricities can be excited when the planet is still in the disk through these planet interactions.
Uh-huh.
And then the other one is that they are migrating due to this idea of coplanar high eccentricity migration,
Yes.
driven by a massive companion that we are not seeing there.
Ew.
So if you ask me, then how can we distinguish between these two mechanisms?
Yeah.
Well, clearly, coplanar high eccentricity migration needs a companion. So
Right?
if we can find this companion and it's consistent with what you will expect from coplanar high eccentricity migration, then that's the case. If not, then I will be more convinced that this you can excite eccentricities with these planet interactions.
Oh, you're a hard person to convince there. Okay.
Yeah.
Very cool. Okay. Yeah, well, we will cover that. We'll wait a little
Yep.
bit.
Yeah, and a way to detect this companion could be to more radial velocity follow-ups,
Mm-hmm.
or maybe the Gaia data release for astrometric measurements could be useful
Ooh,
here.
right, right, right. Very cool. Yes.
And well, for binary systems, If you go slightly down.
Yes, just reading that a little bit. CLK oscillations.
Yeah.
Mm-hmm.
So the binary systems, they are consistent with an isotropic distribution at the 1.3 sigma level. So this population is consistent with the typical high eccentricity migration mechanisms.
Yes. Cool. Okay.
So that's basically the paper, the main results.
Beautiful.
This different, or maybe you can go down and see the conclusions.
Yeah, let's take a look. We got a bullet of conclusions here. Okay.
Yeah.
Hmm.
So first, we highlight the individual measurements. We see that independent of the eccentricities of the system, all the warm Jupiters we study are consistent with being well aligned with obliquities smaller than 10 degrees.
Mm-hmm.
Then the two warm Saturns that we study, they have slightly more misaligned orbits,
Yes.
having obliquities of 15 to 25 degrees.
Yeah.
We also report the non-detection of one of the system, of the Rossiter-McLaughlin effect in one of the systems.
Yeah.
And that's a product of two things. One is that the V sin I there is small,
Oh,
which
right.
produces a small amplitude of the arm effect.
Right.
And the second one is that the transit is grazing, meaning that the planet is crossing right at the edge of the stellar disk.
Yes.
So the impact parameter of the transit is 0.9. So that also produces a low amplitude.
Okay. Okay. Mm-hmm. All right.
Then, uh, as I just mentioned, based on figure 7, the obliquity of the Gaia's giants around single stars seems to be correlated with the orbital eccentricity,
Yeah.
but not in the way you usually would think. It's actually
That's true.
the other way. So obliquity decreases with increasing eccentricity.
Yes. Mm-hmm.
Then deriving the distributions of these different populations, we show that warm Jupiters are statistically more aligned than the hot Jupiters.
Yeah.
You remember, I
Yep.
think was figure 5.
Yes.
Yes. Or 4, yeah, based on the measurements from figure 4.
Yeah.
So the tail of the distribution for hot Jupiters is basically isotropic, but then you don't have any misaligned warm Jupiter around single stars.
Yes.
So
Okay.
this implies that these two populations are different and they have different formation mechanisms.
Uh-huh. Uh-huh. Sure. Mm-hmm.
And also, when deriving the distributions, we show that the Saturns are slightly more misaligned than the warm Jupiters.
Mm-hmm.
So maybe they are also a different population that's been formed by a different mechanism.
Yeah, a little bit larger. Yes. Okay.
Yes, and finally, I think we didn't mention much about binaries, but basically the obliquity distribution for hot Jupiters around singles stars and binaries is roughly the same, and it's pointing towards a similar violent and chaotic formation mechanisms for these
Right.
populations. Basically, high eccentricity migration
Yeah.
driven by the binary companion.
Yes.
And warm Jupiters around binaries, maybe they all also form in a similar way, but the statistics there are low, so we need more measurements of obliquities around binaries.
Okay. Very cool.
So
Whoa.
these are the main conclusions of the paper.
Very nice. Beautiful work, Juan. Beautiful work. Dr. Juan.
Thanks.
Dr. Juan.
Thanks.
Very lovely. Oh, wow. Okay. You touched on it a little bit as we went through,
Mhm.
and I'll push on it a little bit. In where do you think we go from here, given the published article? What would it take to get 80, a sample of 80 instead of 12s or 8? What are we at 80 of these? Are there any new telescopes coming online that may be able to increase the population significantly? We had a couple of degeneracies there, and what do you think it will take to resolve those?
Mhm.
How do we get more periods so that we can convert lambda to psi?
Yeah.
Where do you think we go? Where do you
Yeah,
think we
great
go?
questions. So first, there are definitely telescopes coming online that will be will improve these results significantly. First, I can think of ELT.
Okay.
uh, and the Andes spectrograph, you will have more precision. So you can measure this even for maybe smaller systems.
Yes.
Because now we've been talking about uh,
Meter per second.
Jupiters and Saturns.
Uh-huh.
With espresso, you can actually push the limits towards
Woo.
sub Saturns and
Uh-huh.
Neptunes.
Mm-hmm.
And then with ELT, you can maybe push that towards the super Earths and mini Neptunes.
Wow. Okay. Exciting.
Uh, yes. And about rotational periods, actually, what you can do here, maybe with Plato, you will have the precision to measure
Oh, yeah.
rotational period for the Plato targets.
Uh-huh.
So maybe in the future, measuring obliquities of Plato targets will be valuable.
Okay. Mhm. Multi-instrument attack.
Yes, exactly.
Very cool. Well, it's going to be really exciting over the next couple of years to see this develop, and you're certainly in a good position to be able to study that over the next several years. So very cool.
Yes.
Very nice. All righty, and that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye.